Good evening, everyone. Thank you all for coming. My name is Alec Ray. I'm a mechanical engineer on this project. This is a senior robotic submarine project, otherwise known as RoboSub. So this project, when it started, we were originally going to go to a worldwide competition. At this competition, when we started, we really did not know that much. We knew there were certain tasks that we had to do to complete, such as going to certain locations. We knew how to be waterproof, we knew how to be autonomous, things along those lines. So we kept working toward those things. As we found out more information, we found out it's going to be during the summer. As all seniors, we realized we're not going to be able to make that. So we decided, thankfully during that time, Dr. Rumbaugh and a few other professors were working with the Department of Conservation, Natural Resources to look at lake exploration, figure out fish that are at certain depths, and be able to explore like fish habitat and things along those lines. So thankfully, that came in right at perfect timing, and as a team we decided to change our focus to that, and then to lake exploration. Alright, so the goals of our project was to have a waterproof electronics housing, keep everything dry and safe so that none of the electronics short out. We want to have full position attitude control on all axes. We know exactly where we're going at a time, and basically say where we want it to go, and it goes there. An active control system for correcting for disturbances. Basically, if something got bumped in the water, a current, wherever it is, basically auto-correct and tilts itself back up. Another thing is return to surface on system failure. So basically, it had to be positively buoyant so that when, say, electronics cut out halfway, 20 feet down, wherever it is, it would just rise to the surface and it could be retrieved by whoever's running those tests. Another one is environmental sensing and video capabilities. With that, we want to have a depth sensor so we can tell how far down we're going. And video capabilities, we want to be able to have a camera so we can see after it's pulled out of the water, like what did the bot itself see. Lastly, one of our goals would have a deployable marker buoy so that it would go to a location, go drop off a buoy, and then later on a team can go to that marked location. So next, looking at the physical robot itself. So this project was actually inherited from our 2018 RoboSub team. As you see in the top right image, that was their design, all the thrusters, chassis, everything like that. So with that design, it was negatively buoyant, which I just mentioned, positive buoyancy was something we needed. Another problem with that design was the problems overheating. So it was homemade in-shop circuit boards. Another issue was it wasn't waterproof. It was nicknamed Bubbles because of that. The other thing was it had 8-thruster navigation, and originally moved to a 4-thruster navigation, as you can see. So basically with that, we scrapped the whole thing except the chassis itself, which is the black part on there, which is high density polyethylene, and then on the bottom is the aluminum portion.
I'm Matthew Lamberson, mechanical engineer on this team, and I'll be talking about our electronics enclosure, as well as how we managed to waterproof it. Now to start with, what we inherited from the previous team was a transparent acrylic tube which had machined aluminum flanges on either end. There was a machined end cap at one end that allowed the connectors for the electronics to enter the robot, and a machined aluminum end cap on the other end that also had a transparent acrylic dome, which would allow a camera to stick out. Now, this had, as was mentioned before, the problem of it leaked, and additionally, because we wanted to include more electronics in our design, we were going to need a larger tube. As a result, we switched from the transparent acrylic design, which was visually appealing, but it was not a very flexible type of design. PVC, which is what we have used now, as you can see, the white on the tube. That is much more flexible as far as possible inner and outer diameters. It is more flexible in terms of length, and it's significantly cheaper. That's why we decided to use it, and it has worked well for our purposes because it has very similar physical properties to the transparent aluminum. It has not had any problems with the pressure so far. In addition to that, on either end, instead of having the machined end caps, we have these white flanges that you can see there. Those are 3D printed plastic, and in the future, we would like to see those replaced with machined aluminum because these are somewhat porous and can allow water inside of them, though not inside the tube. As far as waterproofing, like I said, one of the most important things that we can do on this project is ensure the electronics do not get wet while it is being tested or used, because that would most likely destroy the robot and a lot of hard work and expensive materials. In order to implement this, we had two end caps on either side that were attached to the flanges that I mentioned before. These are transparent acrylic, 1/4 inch thick. They are laser cut, so they are very precise, and they do not have the jagged edges that would often be associated with cutting with more typical tools. You can see this first one, which is there on the left and the top. That one has a groove that allows the dome to be secured onto the front. We are also using a camera, so we want that camera to have the maximum possible field of view. That's why this dome is necessary. The back has these holes for connectors. The connectors allow the servos and thrusters to connect to the electronics that control them. These connectors, as I have mentioned down below, they're off-the-shelf connectors. That means that they are IP67 rated, and that means that they can be up to 1.5 meters submergent, about 5 feet, for around 30 minutes. This is not what we want. We want to go to at least 10 feet, preferably 20 or 30. So we've had to do some of our own work in order to ensure that the tube and the connectors are waterproof. This includes using silicone sealant and high vacuum grease to hold them in place and to keep water out. This has worked very well so far. As you can see there at the bottom, we've sent our robot to the bottom of the recreation pool here, and it has not leaked with our recent testing. We believe that it can be waterproof to more than 10 feet, though we've struggled to find a place where we could possibly test it at more than 10 feet. Another interesting thing that we've had to do is we use servos in order to control the angle of our thrusters. You can see the blue plastic down here below the thrusters. Those are the servos. These are IP67 rated. Like I said, that can only go to 1.5 meters without allowing water in. And in order to increase this depth rating, we filled them with mineral oil, because mineral oil is incompressible like water, which means that when the water pressure pushes in, if there were air in there, the air could escape and the air could compress inside the housing, which would then allow the water to seep in. Because you don't have that compression on the housing, you also don't have the water seeping in. And that has allowed us to go to much deeper than the rated depth with these servos without having them leaking and destroying the servos.
Hi, my name is Levi Messenger, and I'm going to be going all over the electronics enclosure. So first thing first, the electronics enclosure is basically the assembly that connects all of the circuitry that we have within the tube. I'm just going to go over the components that are on the board. So right here we have the camera, here's the Jetson Nano and the accelerometer. Right here is the STM32, and underneath that is the battery. Here is the ESCs, or the electronic speed controllers, with the power converter underneath it. And then these are the connectors which connect to the end cap. Now, some of the issues that we had with the old design was due to them being custom PCBs, it allowed for a lot of heat to be distributed in. But with these new ESCs, that's not much of a problem. Now, one thing we had to do with the old tube was 16 inches, and with all the electronics and requirements that we needed, like we needed clearance for USB here and over here. So with that, we ended up needing to extend the length of the tube. We had to end up going to 22 inches. So that just allowed for a little bit more breathing room, and it definitely made it a lot nicer. Some of the things with the design that I did, there's like a pegboard style hole, and that is allowed for easy mating of future parts. So like the STM32 or the ESCs use those kind of holes. Same with the power converter, just kind of clips right into it. So they're all fixed. All the pieces are bolted together, and there's grooves and stuff for wires to get around for just easier access and wiring.
All right, good evening. My name is Mason Wise, and I am a senior mechanical engineering major. Throughout designing the RoboSub this past year, a major design goal was to ensure the RoboSub has slightly positive buoyancy. Initially, after replacing the old electronics housing with a 4-inch by 22-inch PVC pipe as seen here, the RoboSub had positive buoyancy. However, after we implemented 2 flanges, one here and the other in the back, to prevent water from leaking in, our RoboSub became negatively buoyant. So, to make the RoboSub positively buoyant, 2 strips of 7-inch by 1-inch by 1.25-inch subsea buoyancy film were attached bilaterally of the PVC pipe on the upper frame. seen here, and then be on the opposite side as well. Since the RoboSub tilted backwards due to the weight distribution of the electronics within the PVC pipe, we created an adjustable balancing system. This adjustable balancing system consists of a track and 2 carriages. The track is mounted on an upper frame and it runs parallel with the PVC pipe, and the 2 carriages hold a small section of buoyancy foam that can be moved along the track to offset any tilt. So if more testing equipment is added in the future and future projects, the sub will either tilt either forward or backward. It'll be very easy to fix this offset with the tilt using the carriages. So unfortunately, Lauren Mulroy, another senior mechanical engineer, cannot be with us this evening as she's competing at the PAC Championship in West Virginia. So in this slide, Lauren will be discussing the deployable markers she worked on.
One of the goals for using the sub in local lake exploration is to be able to mark a specific location in the lake using a buoy so that a boat above water would be able to find the area. In order to achieve this, the sub would carry a small buoy attached to an anchor by heavy-duty fishing line. When designing a system for this, the first goal was making sure the complete marker system would be neutrally buoyant on its own. The sub has its own balance system, and once it is in the water, there is no way to adjust it. Therefore, the sub must have the same buoyancy while carrying the marker as when it has deployed it. To do this, the anchor and the buoy have equal and opposite buoyancy forces that cancel out when carried by the sub. To release the buoy system, a servo motor was attached to the front of the sub, and a circular 3D printed part was added to the servo head, which was used to then hold and release both the anchor and the buoy at the same time. This part worked by using the downward force of the anchor and the upward force of the buoy to lock them in place while the servo is in the closed position, and then slide out and be released when the servo is in the open position. The last part of this design was line control. Since we needed the line long enough to be released at a variety of depths, the excess line needed to be secured so that it would not become tangled in the sub. The solution was to use a reel of a fishing rod to roll up the excess line and keep it out of the way of the sub's thrusters. The reel was attached to the anchor and the free end of the line tied to the buoy. The spool release of the reel was then tightened so that a pull force of at least 5 pounds would be needed to unravel it. This ensured the line would only unravel when the anchor and the buoy were released and the opposite forces they exerted on it overcame that drag force. The line then unravels to whatever depth is needed and holds tight once the buoy is at the surface and the anchor is at the lake floor.
My name is Kira Johnson. I'm one of the mechanical engineers on the team, and part of what I did was looking at the robotic arm and manipulator portion of the RoboSub. So one of our original goals was to use a robotic manipulator to allow the RoboSub to interact with the environment around it. However, when we switched the focus of the project from the competition to the lake exploration, we determined that this would be beneficial going forward, but not absolutely necessary for our goals for this year. So the intention was we started some of the design process and some of the modeling, but have left it open for a future team to continue these works going forward. So for our design considerations, we wanted the robotic arm to be located on the base of the sub near the metallic part of the bottom. We wanted it to be completely retractable so that it would be enclosed towards the bottom once the submarine is moving and in operation. We also wanted it to operate while the sub is in a hover mode. So if you're in a lake, it would be essentially still, but fighting currents or drift. We also wanted it to use minimal power from the main battery located in the tube. We wanted the manipulator tool at the end of the arm to work passively so that it wouldn't draw more power. We also wanted to make sure that the arm would have enough stability to overcome any drag forces and it wouldn't snap off while in operation. And like I said, we wanted it to be located on the base if at all possible. So the design we came up with was a simple arm working on a rack and pinion system. As seen in the top picture, the top gear would operate as attached to a servo motor. As the top gear rotates, it would allow the arm part to be extended or retracted as the gear rotates. The mating gear at the end of the arm, as seen here, once the arm is completely extended, would then allow a second degree of freedom, allowing the vertical direction to be explored as well. The bottom image shows the arm from side view, which allows us to have a stability hole. So a rod would be inserted so that as it's not in use, the arm would be located on this rod, and it would fight against any drag forces and keep it from snapping off while the arm is not extended.
My name is Eli Kendrick, and I am one of the mechanical engineers on this team. I was focused on the thruster system. One of the first things we did is we upgraded the thrusters from the previous team. They were using bilge pumps that were recycled and fitted with propellers, but these only had about a pound of thrust, so it was kind of underpowered. Our new thrusters produce about 12 pounds of thrust, so it is definitely overpowered at this point. It can move very quickly. We had to design a mount for the thrusters, which you can see in the bottom right here. The mount allows the thruster to rotate so we can vector the thrust and have more control over the sub. We needed to make sure that it was corrosion resistant because it's going to spend a fair amount of time underwater. So we used mostly plastic or stainless steel or aluminum parts. We came up with a cheap and corrosion resistant bearing design by taking an aluminum shoulder screw and putting in plastic bushings, and that worked quite well. We also used a gear system right here from 3D printed plastic gears that takes the 120 degrees of rotation of the servos and translates that to 180 degrees. So the servo can go from pointing straight forward to either 90 degrees up or 90 degrees down. We also waterproof the servos by filling them with mineral oil, as stated previously. After designing the thruster mount, we then had to decide where are we going to put these thrusters on the RoboSub. We wanted it to be able to move very well in all 6 degrees of freedom, so move in each axis and rotate around each axis. So there were a number of configurations we could have used for this, and we settled on the configuration you can see in the top left corner, with 4 thrusters mounted on the diagonals. We wanted to validate that this orientation would allow us to have 6 degrees of freedom. So we ran a simulation in MATLAB that would test out different servo configurations and show us what the result would be. You can see a scatter plot on the bottom left that shows a bunch of different possible directions that the RoboSub can move. As you can see, there's no big gaps within that scatter cloud, so that tells us that it can move in any direction just fine. The next part of the problem was deciding, okay, now I have this thing in the water and the controller tells it to go in that direction. How do we point each thruster and how much power do we add to each thruster to make it move in that direction? So we came up with an algorithm that was based on gradient descent. So you can imagine if you have a thruster that out to the side that's pointing upwards, it's going to make you want to rotate down to the side. So the ideal orientation of all the thrusters can be thought of as being at the top of a metaphorical mountain. And you are at some other position, your current configuration, that is not at the top of the mountain right now. What you sort of do is you, in the software, you're not actually doing this in real life, but you take each thruster and you kind of wiggle it a little bit. And you wiggle the thrust on it a little bit. You do this using partial derivatives. It's in math. And what you do is you say, okay, I'm going to wiggle a little bit and I'm going to see how this changes the current motion that this RoboSub is going to have. And you figure out, okay, if I move it this way a little bit, it gets closer to being at the top of the mountain. You do that for all 8 of the variables that you're controlling. And you sort of take an average step upwards along the mountain. And that gets you a little bit closer to where you want your orientation to be. You don't want to take too big of a step though, because it's not a linear system. So what's uphill at the moment might be downhill a moment later. It's kind of like the ridge line is curving back and forth. So you take a little step and you start wiggling everything again and figure out, okay, if I move this a little bit further in this direction, it's going to get closer to the top of the mountain. You're just constantly going uphill, and that's called a gradient descent. Eventually you arrive at the top of the mountain. You have a configuration of all the thrusters that's moving you in the direction you want to go. So the algorithm runs this every single time. It's updating its direction. You can run it a couple times a second. This plot on the top right here shows an example of one of the variables as it is climbing your metaphorical mountain. You can see it kind of zigzagging back and forth, and it doesn't quite look like it's converging on something. But keep in mind, this is one of 8 variables, and collectively they're all taking a step up and down together. That might mean that you have to move back and forth as you're weaving along your ridge line. You can see it converged on a value right there. So that is how the thruster configuration works.
Hello everyone, I'm Ben Devarro. I am a senior electrical engineering student. I'm just going to talk to you guys real quick about power. For those of you wondering, this is not a nuclear sub. Uses a 10,000 milliamp hour LiPo battery pack. So this thing's a powerhouse. It's suited our needs very adequately. We were able to power all 4 thrusters and everything at full force for over 30 minutes. It's been sufficient to power the entire system. And then over here's a small table. It shows just the rough current draw for each component. So when all 4 thrusters are activated, it draws 6 each, totaling 24 amps. And then the servos, which controls our rotation for the thruster motors to rotate and steer the sub, they draw roughly 1 amp, and then miscellaneous control boards such as Jetson Nano or other little chips, they draw roughly less than 1 amp. Now, the big issue is, in order to get the 14.8 rated voltage down for components that need less voltage, we decided to use 2 DC converters. So these converters, one is used for the servo voltage and the other for the other electronics, like the control boards. So the DC converters, it steps down the higher voltage to more adequate voltages such as 5 volts. So once this is connected to the battery, it will provide a 5 voltage supply to the smaller electronics and a common ground for the other servos, control boards, and the ESCs. The ESCs, they are the electronic speed controllers. This is what's in charge of controlling how much voltage is used for the thrusters, which then changes the speed at which they spin, thus propelling the sub faster or slower. Overall, we didn't have any issues with the power supply during the pool tests. The power end of things worked very smoothly, weren't any issues there.
Hello, I'm John Brzezinski. I'm a senior electrical engineer on the team. I'll be talking about the electronics and wiring of the sub. So let's just start off with the Jetson Nano, which is what you see on your left. Get my left and right confused now. So you have 3 inputs to your system. That would be your camera, IMU, and pressure sensor, and all that data is taken and mashed into a nice, complicated control algorithm. And then that data is sent to the STM32. Basically, the STM32 demultiplexes that data into 8 signals to each of the servos and motors. For the motors, however, you actually have to go through the ESCs since the STM32 cannot possibly supply the power needed to run the thrusters. You have 2 sensors, you have the Hall effect sensor, which is actually your reset, which is actually your emergency stop. So when you actually hit that, which is this button here, the magnet actually drops down and comes in contact with your Hall effect sensor. So when that happens, like the STM32 sends out data to your servos and motors saying shut down everything, and then the positively buoyant system will make the subsurface and the system is shut off. You have the reset switch. This is actually used to, when you throw the sub into the water, you actually have to hit this just as a startup procedure, just to clear out all the excess code that might actually run. So the external wiring, so we had actually 2 problems. The motors in the front, the thrusters, the actual wiring didn't reach the end cap, so we had to figure out how are we going to waterproof this through splicing. So we use these things called solder steel wire connectors. They're great. So all you have to do is just heat it up, melts the solder bead in the middle, and basically insulates all the copper connection. Just in case we miss something or there could be water maybe, we also decided to use heat shrink with marine 2 epoxy inside of it and heat shrink the whole insulation of that wire together to provide 2 barriers of waterproofness. What you see on the left there is what is called a wet link penetrator. This is used for the motors, or the thrusters, and it basically has a screw which tightens the insulation inside, which provides a nice seal around the insulation of the wire. What you see in the top left and the bottom right are what we use for the servo connections to the end cap. yeah. That's basically it.
I am Peter Meller. I am a mechanical engineer on this team, and I worked with the navigation sensors. So this chip right here is an inertial measurement unit. So this gives us rotation data, and we can calculate position data from the acceleration data that it gives us. So the rotation data gives us 3 different axes: roll, pitch, and yaw, so we can determine where exactly the sub is pointed. We feed that into our control algorithm to see what needs to happen to get it pointed in the direction that we want. We can get position data through a process called dead reckoning from our acceleration data. So if you guys are familiar with any calculus or physics, if you integrate acceleration, you get velocity. If you integrate that again, you get position. So it does introduce some error each time you integrate. So that's why we also have a pressure sensor, which is not pictured on this slide. That provides a more accurate depth reading than our IMU could give through dead reckoning.
Hello, my name is Aaron Myers. I'm the computer engineer on the team, and so I'll just be talking about our control architecture and sort of how we've designed from a broad perspective how we get the sub to move where we want it to go. So pictured here on the right, you can see the sub and how we've defined our coordinate axes. So obviously Z is up, and then X and Y. And so just going along, starting from the left, so we have our X, Y, Z, and then rotation around the X, Y, and Z axes, the pitch, roll, and yaw. And so each of these is given a set point, where we want to go and what rotation we want to have, and it's fed into a proportional integral derivative controller for each one of these. These each have gains that are derived empirically from testing the RoboSub in the pool. So then we merge all of these values together into a single packet of data that's sent to the algorithm Eli described earlier that determines how to point the thrusters and what amount of power to provide to them. Then this is sent along as a command to the STM32 microcontroller, which then sends the signal to power the thrusters. So once the thrusters move the sub in a given direction, that updates the information that the inertial measurement unit gets in terms of the acceleration of the sub, as well as its orientation, and this also updates the depth of the RoboSub that the pressure sensor senses. And so then this is combined into a pose, and the pose is basically just a way of describing the orientation and position of the RoboSub. It's then sent to a quaternion conversion node, which a quaternion is just a mathematical form of describing position and rotation, and then that's split off into each one of those things, and the control loop repeats then.
So we have 2 main software packages running. I'm Nicholas Sparks. I was in charge of software, but senior electrical engineer. So we have the software running on the microcontroller, and the microcontroller really, its purpose is to split the data, send it to the motors, but also it acts as a safety. That e-stop switch, we wanted to test it for its states very closely, so we wanted a small enclosed system that didn't do a ton. We want this to be separate from our main processing system. So that's what the ESC does. It was coded in Arduino. It manages those 8 motor outputs, takes it as a serial input, sends it out, and then is constantly listening for that e-stop switch to see, okay, do we have to shut off the motors? Are we in this point where the user is saying we have to stop? Then we have the software running on our Jetson Nano. Now, the Nano is a small portable piece of hardware by itself. We wanted to pair it with an operating system that allowed us to easily develop with it. We decided upon Ubuntu Linux. This is a software distribution that comes with a GUI, so it's easy to debug. And that was widely used in small robots. On top of that, we have Robot Operating System, which functions as an interconnect between the code we wrote in both Python and C. And then finally, we have our small individual pieces of code. Some of them we wrote, some of them we were able to find online. This was one big advantage of using Robot Operating System, is the community is large and it's easier to find stuff, pre-made packages for it. So in the end, the RoboSub, it's now waterproof. We completed, this is kind of a list of our design goals. We have the RoboSub waterproof. We didn't think that'd be as hard as it was. It turns out it was a bigger challenge than we originally thought. It's finally waterproof. The next team can go forward sleeping easy. Active control system, correcting disturbances. We got this mostly integrated. Software-wise, it's all there. There's some more debugging that needs to be done, as well as some tuning. Full position and attitude control on all axes. We are having a little bit of trouble tracking our position using dead reckoning, but this is, again, mostly implemented in software and just needs a little bit more work to get it past the finish line. Return to surface on system failure. This is just achieved by positive buoyancy. We do the sub is positively buoyant, so if it, for any reason, it shuts off, it will naturally float to the surface. We are able to sense our environment and take video of it. And finally, the deployable marker buoys, the hardware has all been built for that, but it hasn't been mixed with our electronics or our software yet. So with that, do you all have any questions?